Okay, so we're going to continue drawing some examples of Lewis structures. The next molecule that I'd like to look at is sulfur dioxide, SO2. So notice how I named that. It's a covalent molecule of two nonmetal atoms, sulfur and oxygen. So we use prefixes. This is sulfur dioxide. All right, so valence electrons. Sulfur is in groups 6, so it has 6 valence electrons. Oxygen is also in group 6, but we have 2 of them. So we have a total of 18 valence electrons. How are we going to arrange these? Sulfur is the first atom listed, so we'll put it in the middle, and we'll attach the oxygens to it. Again, it doesn't really matter where you put the oxygens right now. You can put them on left and right, top and bottom, left and top, whatever you want. But we do have to glue them on, so we're going to go ahead and use a pair of electrons to attach each of the oxygens. That used up 4 of our valence electrons. Now here's the first case where it kind of matters. We do want to start adding lone pairs to the outer atoms first. So that means the oxygens. So we've had 2, 4. We'll start with this one, 6, 8, 10. That gave that oxygen 8, so we're going to move on to the other oxygen. 12, 14, 16. Okay, now both oxygens have 8. We've used 16. We get 2 more, and so we'll go ahead and put those now on the sulfur. Okay, but count, we've used 18 valence electrons. Oxygen looks fine on both sides. Sulfur, however, only has 6 electrons right now. It says, wait a minute, oxygens get 8, why don't I get 8? Okay, so we're going to bring in this new role or step that we haven't talked about yet. If you run out of electrons before everything has an octet, what we're going to do is share more. Remember, it's sharing that sort of lets us get away with fewer electrons than we would otherwise need. So right now we're sharing just 1 pair between each sulfur and oxygen. But what happens if I take this lone pair, which I can only count for this oxygen right now, and I move them in here so that I can count them for the oxygen and the sulfur. So I'm going to redraw this so we can kind of see what happened here. So now I have 2 pairs of electrons in here. Everything else stays the same. Okay, and if we sort of start looking at who has what, I can still say that this oxygen has 8. I can now say that this sulfur has 8, and of course this oxygen still has its 8. So this is how we're going to distribute the electrons to give everything an octet in the structure. We want to redraw the bonding electrons as lines. So we're going to have sulfur, but now we have something new. We're not sharing just 1 pair of electrons, but 2. So we show 2 lines to represent what we're going to call a double bond. Let me clean that structure up a little bit. Sorry, it's a little ugly. Okay, let's try that again. Here's my double bond to oxygen. Single bond to the other oxygen. So here's my final Lewis structure. When 2 atoms share 4 electrons instead of just 2, we call it a double bond, as compared to a single bond that we have over here. Notice that each atom still has 8 electrons. That's important. Okay. And what we know about double bonds, essentially we're putting more glue in there, right? So double bonds are generally stronger than single bonds. Okay, but it's important that you only make double bonds sort of when you have to. So the procedure that we've outlined where we start with adding the lone pairs to the outer atoms first, adding to the central atom if you have extra, And then you check, does everything have an octet? And if you still don't have octets on everything, then you can go ahead and start forming double bonds. And we'll see the next example is actually going to have what we're going to call a triple bond. Okay. All right, so let's go ahead and look at a new molecule. And actually, this time we're going to add a couple new things. We're going to look at a polyatomic ion. So this is not one of the ones I've asked you to memorize, but it illustrates something interesting about Lewis structure. So we're going to go ahead and do this one. This is nitrogen bonded to oxygen with an overall plus charge. Okay, so let's count our valence electrons. Nitrogen has 5. Oxygen has 6. It's in column 6. Now what do we do about this guy? Remember, a polyatomic ion means that the overall has a charge. How did it get that charge? If it's a positive charge, it got it by losing an electron. So we had 11, but we have to take away 1 electron because of that positive charge there. So total, instead of 11, we have 10 valence electrons. Okay, this one, how are we going to put them together? It's just 2 atoms again, so we put them next to each other. Doesn't matter the order. We'll glue them together with a pair of electrons. Start adding the rest of our electrons as lone pairs on the outer atoms. And it doesn't really matter which one you start with in this case. There's our 8. We'll go ahead and put the last 2 on oxygen. All right, so nitrogen looks pretty good. It's got its 8, but oxygen only has 4. That's not really fair. So we need to share more. Now, what do we want to do? We want to take sort of from nitrogen to share so that we can share them with oxygen. We can do it once to make a double bond, but that's still not going to be enough. We're going to actually need to do it twice so that each thing can have 8. So let me redraw that. So these guys aren't there anymore. They're now shared. And we have a total of 6 shared and 1 lone pair on each of the nitrogen and oxygen. So let's count, make sure we haven't messed up here. We have 2, 4, 6, 8, 10 total electrons, 8 around the nitrogen and 8 around the oxygen. So this is going to be our Lewis structure. We're just going to clean it up a little bit here and put a triple bond now between the nitrogen and the oxygen, lone pair on the nitrogen, lone pair on the oxygen. And then we have one final little thing to deal with. One of my rules is that if you have something that's an ion overall, go ahead, we're going to put it in brackets and indicate the charge on the outside because we want to remind ourselves why there's 10 electrons and not 11. So this would be our final Lewis structure for NO+. And again, let me emphasize that this, maybe do it with green, is a triple bond. So when you share 6 electrons total, that's called a triple bond. And as you might guess, a triple bond is even stronger than a double bond. Okay? And you can kind of think of it, we put more glue in there, it's going to hold better. Okay, so there's 2 last molecules I want to show you and kind of compare them. Not sure why that won't go all the way up. Okay, so I want to look at the peroxide ion, O2 2-, and compare that to oxygen. Okay, so it's going to show a couple things. There we go. Okay, so let's do the peroxide ion first. So we have 2 oxygens. They're each in group 6, so that's 2 times 6. Now what about this -2 charge? Okay, minus charge means it's gained electrons. So in this case, we're going to be adding 2 extra electrons to give us a total of 14 valence electrons in this structure. Okay, so 2 atoms, we'll just put them next to each other. glue them together with our electrons, start putting lone pairs. So we've used 2, 4, 6, 8. Move over to the other oxygen, 10, 12, 14. We have 8 electrons around each oxygen. We've used our 14 valence electrons, so everything looks good. We'll just clean this up by putting our single bond between the 2 oxygen atoms. Now this is not the oxygen we breathe. This is the peroxide ion. So we're going to emphasize that by go ahead and showing the charge, right? We'll put brackets around it and show the charge. So we see that the peroxide ion has a structure kind of like fluorine in terms of the electrons, but it's got a -2 charge, and we have a single bond between the 2 oxygens. Okay, not really sure why that's showing up at the moment. Can I get rid of that? Sorry about that. Okay, so let's look at oxygen atom, or sorry, oxygen molecule. So we have 2 oxygens, no charge. So this just has 12 valence electrons, not 14. Okay, we put the oxygens next to each other, glue them together, start putting our lone pairs, 2, 4, 6, 8, 10, 12. Uh-oh, I ran out of electrons before everything had an octet. What do I do in that case? I have to share more, right? So I take a lone pair from the one that has enough, share it into the bonding space to help out the other guy. And for oxygen molecule, I can get octets if I make a double bond. So the oxygen that we breathe is the O2 molecule. It has a double bond. And again, this sort of also shows why oxygen wants to be diatomic. Okay. It also, we've mentioned that double bonds are stronger than single bonds. We can even start to explain some chemistry here. So we're going to look at reactions a little bit later, but one of the types of reactions we look at are called oxidation reactions, reactions with oxygens. So oxygen, O2, is a good oxidizing agent, but peroxide ion is an even better oxidizing agent. Why? Well, it's harder to break the double bond in the O2 molecule than to break a single bond in the peroxide ion. So peroxide is a very good oxidizing agent. It's able to react well with other things because it has a bond that's very easy to break. Okay, so that finishes off all the examples that I wanted to do that show you how to count the valence electrons, arrange the atoms, glue them together, put the lone pairs on, and then adjust, either share more if you need to, and then draw the lines for the structures. So now you can work on the examples in your packet that you get to try.